Let's continue. So we have been looking at our sampling network. So we essentially started with this simple rack and hold, and then we started to see the possible non-idealities when we implement this switch using a MOS transistor. The first non-ideality we noticed was that switch has a finite on resistance, and that this on resistance was actually dependent on the input voltage, right? And what was the consequence of this dependence? Yeah, we saw that when we try to sample a time varying signal, this results in non-linearity. So we'll say when we have time varying signals, we will have non-linearity. So the solution we saw was to try to keep this omega RC product to be as small as possible with respect to 1. But beyond some point, you can't reduce it further. We saw the limitations. So to get a better linearity, a solution was to use the gate bootstrap switch, where you try to keep the gate to source voltage constant. And then we looked at the fact that this on resistance also generates some random thermal noise. Because of this, the sampling capacitor, along with sampling my actual desired input, also samples this noise. And what is the mean squared value of this noise? We collect it was kT by C. And can you make any comment about the power spectral density of these noise samples? It is white. Under what condition? The RC time constant is much smaller than the time for which the switch is on. So under this condition, we can say the power spectral density is flat, but this result is good even otherwise, right? Now, unlike non-linearity, where you could do a couple of these things to reduce its effect, noise is something fundamental. There is really not a lot you can do about it, right? So it's a fact of life. We have to live with it. Only thing you can do to reduce noise is to increase the sampling capacitance. So you need to know how to deal or analyze noise, and make sure that you design your circuit so that even in presence of this noise, your circuit has the final required effective number of bits. That's all you can do. Now in the last class, we also looked at the other non-ideality that happens when we try to turn a MOSFET or MOS switch from on to off. So we saw that when the MOS transistor is on, there is some channel charge, and the issue was that this channel charge was non-linearly dependent on the input. Let me use a different function, maybe some non-linear function g of input. So which means when I turn the switch off, this channel charge has to go, and this essentially has two parts to go. The exact fraction of the charges that goes on either sides depends on the relative impedances looking on each side. Now we really do not know what is on the input side. It depends on what is the previous circuit and so on. So one thing we can comment for sure is that some fraction of this signal dependent channel charge can get injected onto the sampling capacitor, and that directly adds to nonlinearity. So what was one solution for this? What did we do for to make sure no charge gets injected? We need to make this impedance infinite, and we did this by basically opening this side of the capacitor. So let me draw it separately maybe. So what we did was this. I'll use ideal switches. So instead of grounding this guy all the time, we basically had a separate switch. Let us say the sampling phase, I'll call it phi 1. We opened this switch much before opening the main sampling switch. So this was the bottom plate sampling, and with this way we kind of get rid of signal dependent charge injection. Of course, this is not the only way to tackle charge injection. In your practice set, I'll give you a couple of other techniques you can use, but unlike most of them, this is one short way to eliminate signal dependent charge injection, because we are essentially making this impedance open, so nothing should ideally flow. But then we noted that in practice there can be a small off capacitance. So let's say I draw it like this. Because of this, this impedance will no longer be infinity. It will be finite but still a large number. So the charge injected from here will not be exactly 0. So you can still have some signal dependent charge. But then we notice that if I look at the charges stored on these two plates, some of these two charges didn't have any signal dependent charge component. So to convert this charge to an equivalent voltage, we decided to ground this plate of the capacitor and look at this voltage, which was as good as minus input, minus V in for all practical reasons. And we also recognize that we cannot turn the switch on when both these guys are on. So we need to activate this switch only after turning off both these switches. So which means these clock phases phi 1 and phi 2, they have to be non-overlapping. Right? And we also saw one simple asynchronous logic to kind of generate these non-overlapping clocks. So essentially what happens is this, first we have both these switches phi 1 and phi 1e to be on. So we'll have something like this. Then we turn off this switch first. So the circuit will look like this now. Now of course when you turn this switch off, there can be some charge injection from this switch, but that is not a major concern because charge stored in this switch has no signal component. You only worry about charge injection from the switch that directly is connected to the input. Okay. So this is what you do, and then you turn this off. But of course now when you turn it off, because of the off capacitance, you have something. So finally what we do is this, we ground this guy, and I will not show this, it's open, let's not confuse it. We look at this voltage. We also saw if we were to process this voltage, ideally we should not be drawing any current from this guy, because the moment we draw any current, we are losing out the charge stored in the capacitor, we lose out the actual input information. So we can either use an open loop buffer, or a better deal was to do the following. We saw that if you have op amp, you guys will learn how to make op amps. Some of you might already have learned. So let's assume you have already made a good op amp. We observe that if I put a capacitor in negative feedback across an ideal op amp, I can measure the voltage across this capacitor without drawing any current from this. So then the thought process was, why don't I try to transfer this charge to this capacitor so that I can process this voltage. So that basically led to this equivalent circuit. So this gave rise to the switched capacitor amplifier. And let me see, this is the sampling phase phi 1, this is the processing phase phi 2. Now of course when we analyze these switched capacitor circuits from now on, we will only look at this equivalent circuit and this, because all these intermediate things, they are existent for preventing the signal dependent charge injection, and we know for a fact that if I do this, there is no signal dependent charge injection, so we will not worry about charge injection or these things, we will only focus on these. Okay.
Just to reiterate, the use of op amp is to not lose the information.
Correct. Basically someone has to provide a current, use op amp to provide a current, that's all. Cool. So now we can draw the complete circuit in both phases. So we have the same thing, the input is sampled in clock phase phi 1, this is early version, and then in phi 2 you do this, and then you have the capacitor here, and recollect that I also have to reset this capacitor every time so that it is starting fresh. So again, the way this worked qualitatively is this. In clock phase phi 1, this capacitor is sampling my input V in. So what is the charge stored on this plate? Yeah, this plate has plus CV in. So obviously this will have minus CV in. And in the clock phase phi 2, we are grounding this and connecting it. So this is 0, this is 0. Voltage across the capacitor is also 0. So it's losing its entire charge, and the charge basically goes here. So that means the charge on this plate of the capacitor is plus CV in. So the final output voltage, which is also equal to voltage across the capacitor in this polarity, is basically the charge, which is C times V in by the capacitance. Okay. Fine. So now here we can make some minor modifications. So here if I look at this thing, the op amp is connected to my sampling network all the time, right? But when do I actually need this op amp? Do I need the op amp all the time, or when do I need the op amp actually? Only in the clock phase phi 2 we need the op amp. So instead of connecting it all the time, I can basically free the op amp in one clock phase at least. So that leads to this minor modification. So nothing changes here, it's same old. We are sampling it as usual. Now here, instead of connecting it to the op amp all the time, I put a switch. And similarly, if I look at the capacitor CF, this capacitor in clock phase phi 1 is getting reset to ground. It is only needed to be connected across the op amp in the clock phase phi 2. So again, I don't have to use the op amp all the time. I can make sure that I connect this capacitor only during the clock phase phi 2. Clear? So instead of making this connection and doing it all the time, I'll clock it like this. So this will be clocked at phi 2. Okay. And again, CF has to be reset during the clock phase phi 1. So I should add 2 more switches to reset it to phi 1. Something like this. Is this clear?
When we use this first switch for turning on the op-amp,
This one.
was it sufficient? Like, why we require 2 more switches for on the hard filter?
Yeah, basically the point is you can share basically these switches and these. It's fine. That's also fine.
If we would have, we will turn on the switch too, we will directly connect the CF in the feedback.
Yeah, but the deal is it is not about connecting CF. The point is I want to make the op amp free during clock phase phi 1. Here you see that the op amp is always connected. I don't have any free time, right? Here at least you see that the op amp during the clock phase phi 1 is completely free. Again, why you might want to do it, there are a lot of reasons. One thing is, like you're saying, maybe in clock phase phi 1 you don't need the op amp. You can maybe power it off. We typically don't do that in practice, but other thing you can do is, as we will see going forward, the op amp will have a lot of non-idealities. So if the op amp is free in one clock phase, we can try to do something to correct for the non-ideality in that phase when the op amp is free. Seems logical? That's all. But otherwise the equivalent circuit in both clock phases, phi 1 and phi 2, will be same here.
In practice, CF should be made equal to C, right?
It depends. Let us say you want to have output to be exactly equal to input, yeah, CF should be C. But if you want, sometimes you might want to.
The information reduces by a factor of CF.
No, if you make CF to be smaller than C, you get better, right? I mean, as we'll see, this will be used for making bigger filters. We'll see going forward. Okay. Cool. So here, if I actually notice, in either of the two circuits, let us say this is my main clock. So I'll call this as phi 1, phi 2 and so on. Again, just to remind you, the actual clocks phi 1 and phi 2 will be non-overlapping like this. Okay. This is how my actual clocks will look like. For easier, understanding and representation, I am showing it like this. Okay. So now, maybe I'll push it down. So here, if you notice, when is my input getting sampled? At the end of clock phase phi 1 is when my input is getting sampled. And when is the output available? It's not at the start of phi 2. Phi 2 is when you are doing it. So in principle, at the end of phi 2, it is available, right? I mean, now we have ideal switches, but if it's real switches, it will take some time to charge, discharge, blah, blah, blah. So in phi 2 is when we are doing the amplification. So at the end of the clock phase phi 2 is when my output is ready to be processed. So I will say Vout is ready here. Okay. So now you see that there is about half clock cycle of delay. From the time my input is sampled in my circuit to the time my output is ready.
So is there any significant delay between phi 1 and phi 1e?
Not a lot. It's just few hundreds of picoseconds of delay.
Likely happen at when phi 1e moves.
Correct. Yeah, that's what for these analysis we'll ignore phi 1, phi 1e. Again, the delay usually if it's phi 1e, phi 1 might be few hundreds of picoseconds delay. That's all. This is just for our bottom plate sampling. So again, we'll not consider these effects because it's fine. Good. So as of now, as you see, there is half clock cycle of delay. So let us say I don't want to have the delay. Right? So now here, if you see, we have a delay because input is getting sampled during one clock phase, and it is getting amplified, or this guy is transferring charge to CF in another clock phase. Now, if I don't want to have any delay, in words, what do you think I should be doing? Right now there is a delay because two operations we have to do. One is sampling, other is transferring the sampled charge to CF. These two are happening in two different clock phases, resulting in this half clock cycle of delay. Now if I don't want to have any delay, what should I do? I should have both of them happening at the same time, right? So that leads to this variation. So first let me show the op-amp first. Let us say I want everything to happen in phi 1 itself. Okay. So this is the op-amp. I have the capacitor. When should I connect the capacitor now? In which clock phase? I want everything to happen in phi 1. So this is the main clock phase where the action is happening. So which means when will I reset this capacitor? In the other clock phase, phi 2. Okay? Sorry, where it's supposed to, phi 2 supposed to be? No, yeah, it is not phi 2 same as phi 1. You think of it like this, two operations are there, sampling and transferring charge to CF. Both should happen at the same time. That I am taking it to be some phi 1, that's okay. In some clock phase phi 1, this is happening. So which means now in which clock phase I should sample the input also? In the same clock phase I should sample the input. So I have this. And remember, I should also be transferring the charge to CF in the same clock phase. So what should this be clocked at? 1. So this is Vn. So which means in the other clock phase I should reset this guy. Okay. This is another variant of the same switched capacitor amplifier. So one difference in the circuit is this. Let me redraw it neatly. So the way it operates is this, right? So now in clock phase phi 1, let me draw the equivalent circuit. So this is what we have in the clock phase phi 1. Fine. Okay. So now tell me, at the end of the clock phase phi 1, what will be the voltage sampled across C? End of this clock phase, what will be the voltage across C? V in. So which means, what is the charge I am drawing from the voltage source here to charge the capacitor? I am effectively drawing a charge of C times V in. And remember, for capacitor to get charged and develop some voltage, charges must flow in a closed path. So it flows here, and where is the charge flowing now? Directly going to CF like you wanted. And where is it ending? No, it should come to ground, right? Where is it going to ground? Huh? It's through the op-amp. This is the op-amp which is providing the current, remember. So we have the closed path through the op-amp. The op-amp will have its own internal ground, which is the same. That's the closed path. So to show the closed path, this is my V in. Clear? So now you know that a charge of C times V in, I will not show this loop, hopefully it is understood. So now we have this charge of C times V in coming from the input source that goes here. So what is the charge on this plate? It's plus CV in. The charge we are drawing is plus CV in, right? So that goes here. Same thing, it goes here and here, right? So what is the charge on this plate now? So what is the output voltage now? Output voltage is basically the charge is minus CV in. So the difference is we have an inverted gain. Yeah. So again, if you look at the earlier delayed amplifier, so here what I was doing is I was basically taking the charge CV in one clock phase and charging my capacitor, and then after getting this charge from V in the other clock phase I was going and transferring this charge. Whereas here I am drawing this charge CV in from the voltage source and transferring it to CF at the same time. Is that clear? I mean, this is basically analogous circuit is the inverting amplifier that we have seen with op amps, right? If this is V in and this is R1, what is the current? V in by R1. Now this current is obviously being forced to flow into this feedback resistor, and that develops the voltage, blah blah blah. Same thing is here. Okay. So in the earlier case, we had a proxy, we were taking the charge from V in and then dumping it separately. Here we are allowing a continuous streamline of, stream of thing to flow. Okay. Cool.
About the
Delay of what?
delay of the op-amp.
Yeah, I mean right now we don't worry about it.
Because in earlier thing we won't consider.
In both cases, op-amp will have delay.
Because we are when taking the output at the end of phi 2.
Here also we take at the end of phi 1. So here we do it at the end of phi 1, right? That's all. This is phi 1. We take at the end of phi 1.
The value of the voltage that was there at the capacitor C,
Mm-hmm.
value of voltage across the capacitor C, won't be the same as the value of voltage across the capacitor C at
Correct.
the end of phi 1.
Voltage will be different, true.
So we should take the value sometime after.
I mean, just at the end of phi 1 you can take. I'm not following your argument. So basically, this is the equivalent circuit during the clock phase phi 1. So if my op amp makes sure, if my op amp is fast enough so that the output settles here, yeah, fine. We have to design your op amp. Right now your op amp is ideal, so it's responding instantly. But of course, in practice, you design your op amp to be fast enough so that the output settles like this within your time. As of now, it's all doing this. Full. So
Are we still sure that this new circuit will compensate the channel?
okay, again same thing, right? So if this is the case, so channel charge is problematic from this switch. So what if you do bottom plate sampling as usual, what switch you turn it off first? I mean, input is sampled like this, so you make sure this is turned off. Same thing, right? Whenever you have a switch connected to the input, you will have charge injection, signal dependent charge injection. The solution is bottom plate sampling. We have the other thing and turn that off a bit earlier. So again, in the last class, recollect, we also looked at how to analyze switch cap circuits. Again, to reiterate the point, like any lumped electrical circuit, you can use KCL. That's what you should do. So you write this summation k, ik of t to be 0. Now just that if you are looking at switch capacitor circuits and if you have ideal switches and capacitors, in switch cap circuits the branch currents will all be currents through capacitor. So it's going to be summation k, some ck dvk by dt be 0. Now again, if switches are ideal, op amps are all ideal, voltages will jump instantly. So if I look at two clock phases, let us say if I look at voltage Vk, let's say it jumps like this from one phase to the other. So let me call this Vk in the previous clock phase. This is Vk in the current clock phase. So how will I mean if I plot the current Ik, how will it look like? It will be an impulse. What will be the area of the impulse? Ck times the difference between the voltages. My voltage in the current phase, voltage in the previous phase. Right? So again, if I do this, then this becomes Ck times Vk in the current phase minus the capacitor voltage in the previous phase, sorry, times delta of t, right? This is the current. Now of course, you don't worry about anything and just say delta t, I mean you don't consider this and equate only this term to 0. And if I take this term, this basically is summation k delta qk. So that's basically saying that I have summation k ck times the voltage in the current clock phase, the same as the voltage in the previous clock phase. So just that, as usual, you start with KCL. If you have ideal switches and capacitors, the currents look like impulses. So KCL boils down to simple charge conservation. But otherwise, this is the ultimate mantra for solving any lumped circuit. Right? Again, you see, right? If you do KCL and if you have impulsive currents, this is the area of this impulse. And what is the units of this? Area of this impulse as units of charge. Okay. So that means essentially if I say that I have a current source and I pump in, let us say, phi delta of t of current to a capacitor. In English, what this means is I am pushing in a charge of 5 coulomb to a capacitor. That's all. Okay. So yeah, bottom line, you do charge conservation. So what you do is this. Let us say you are interested in solving the voltage during a particular clock phase phi 2. You look at a particular node k. Say, let's say this is some particular node, I don't know, some x or something. Let us say you have 3 capacitors like this. You look at the charges stored on these 3 plates. This is the current clock phase. You equate it to the charges stored on the same plates in the previous clock phase. So in the previous clock phase, the connection can be completely different. So let us say this capacitor is connected to something, this capacitor is connected to something, and this capacitor is connected to something, I don't know. But still you go and look at the charges stored on the same plates. Is that clear? Again, if you are confused, again resort to KCL, summation of the current is 0. That is basically saying delta Q flowing in each of these branches is 0, and that should get you home safely. Right? So yeah, again, so if you have, let us say, yeah, so here we have assumed everything to be ideal, so things jump instantly. But in practice, when you have finite on resistance and the op amp is not infinitely fast, you will have, like slow changes like this. To capture this slow change, you have to go to KCL and solve either this, or let us say you don't like differential equation and you hate Newton for inventing calculus. You convert it to algebraic equations. So you do KCL in Laplace domain, and then you do this. That is also.
Shouldn't we be starting from charge conservation?
No, why not?
KCL is result of the charge.
No, that is easy to say that way, but KCL is coming from Maxwell's equation. Maxwell's equation is the entire thing governing all electromagnetic things, right? And in Maxwell's equation, if you take whatever Ampere's law, whatever, that boils down to KCL. Okay? I mean, when you are learning KCL, it's easy to learn from charge conservation to KCL, but doesn't mean charge conservation is a superset of KCL. Okay? Maxwell equation, KCL, charge conservation. Yeah. So one thing is, you can also solve using KCL like this. Like instead of drawing the currents and doing this, you can treat it like this. So let us say you have a capacitor charged to the voltage V0. It has an initial voltage, let us say V0, right? How can you model this initial voltage? Yeah, remember that I can always do it like this. Okay, so let us say these are the terminals A and B. Now these will be the terminals A and B. I mean, again, you can, it's not that difficult to see, right? So if I look at the capacitor voltage Vc of t, let's say look for t greater than 0. How do I find the capacitor voltage in terms of the current? If I know the current flowing through the capacitor, how will I find the voltage? 1 by Ic of t dt. So let's say from 0 to t, plus you have the initial voltage V0, correct? Now I am considering for t greater than 0, so loosely speaking I can say it like this. So this I can treat it like this. This has 0 initial voltage, and this is my V0 times U of t. Same thing. So you can use this also to solve our switch cap circuits. So let us say I take our switch cap amplifier. We take it to a next page. So this was the circuit, right? In one clock phase, let us say I sampled it, and the other capacitor was reset. In the other phase, I was transferring the charge to CF. This was the delayed amplifier where we were doing in 2 clock phases. So here, let's say I'm interested to solve for Vout in this clock phase. Again, you try to apply KCL here. So here, which of the 2 capacitors has some initial voltage among these? C. In the previous clock phase, C was charged to V in this polarity. So the initial voltage this capacitor C has can be again modeled like an initial voltage or a voltage in series with this, in the same polarity. Okay, so this is V in times U of t, or if you use Laplace, that becomes V in by S. So now we can solve for this. So now can you tell me what is the current I of S? This is 0. What is this voltage? Minus V in by S. So what is the current? This is the voltage. Huh? What is the, I mean, come on guys, it's simple Ohm's law. Yeah, by 1 by, fine. Sorry, it's not V in of S, I write V in by S. So this becomes minus V in times C. Again, voila, you see that this is basically charge. Again, same thing, Laplace transform for current, it's basically charge. So now this current is flowing here. So again, you can find what is the voltage. V out of S will be the current times the impedance 1 by SCF. So this is basically you get the same thing, V in times C by CF by S. That's what. So this is a better framework because now if you want to see what happens when I have finite on resistance, I can just add the switch resistance here. What will change in my equation now? If I add an on resistance, what will change in this? The current will now have R plus 1 by SC, and then you can solve. But yeah, most cases we will be worried only about the settle value, so we'll ignore on resistance and directly do charge conservation. Oh, the deal is we are looking for a time instant t greater than 0, let us say. The initial condition you treat it as V naught times U of t. There is no true DC, right? It is all after some time. You assume that this is no time greater than 0. So let's look at one example so that we get some practice. So I'll take my standard example. Let's say I draw equivalent circuit in 2 clock phases. In phi 1 I have something like this. Let's say C1, C2. This is, let us say, V in 1. I have another capacitor C3 connected to V in 2. In the other clock phase, let us say C1 is discharged. It's like this. And let's say I'm interested to find what is this voltage V out at the end of the clock phase phi 2. So again, first things first. So I'm interested in finding V out in which clock phase? Phi 2. So which of the 2 circuits I'll try to solve? This circuit is what I'll try to solve. So again, you try to apply charge conservation. Same thing like KCL. You first choose a node where you want to do this. Which node will you choose now? I have 2 nodes. I mean, probably how many nodes I have? This. How many nodes I have in this circuit? I mean, yeah, exclude the ground reference, you just have 1 node. So you look at the charges stored on the capacitors. Let's say this plate. This is the only thing you have. So what is the charge? V out times C2 plus V out times C3. This is the charge in the current phase. You equate it to the charge stored on the same plates in the previous phase. So again, I look at the same plates. So tell me what is the charge stored on the same plates in the previous clock phase phi 1. C2 times V in 1 plus
C3 times V in 1.
That's all. So now you write it, V out is simple, C2 V in 1 plus C3 V in 2 by. So typical confusion, I mean, students might sometimes have this. I mean, when I look at the charge here, why should should I not be looking only at this charge? Why am I looking at this charge? So that is basically an incorrect interpretation of this. So remember that you are interested to find that voltage in one particular circuit. This is the circuit you are interested in, right? So you only look at the currents flowing here, and this current depends on the, oh sorry, yeah, okay, thanks. Again, to make sure you are all paying attention, I did an intentional mistake. So yeah. So again, as I was saying, sometimes the typical confusion is, why should I take only, why should I not, or should I not take only C3, right? So remember, you look at one particular circuit, apply KCL there, which means delta Q flowing in both the capacitors is 0. So this is what you are interested in. So if there are 2 capacitors connected here, you look at the same capacitor charges in the previous phase. Clear? Cool. So hopefully this is clear. So let me move on to something. If you have any doubt, you let me know. Cool. So till now we have seen switch capacitor circuits that basically do this. We have sampled some signal V of n.
We have applied charge conversion on only C2 bit.
No, that's what. Don't look at it plates. Look at a particular node,
No.
right? It's basically KCL, right? We are choosing a node, looking at the delta Q flowing in both sides to be 0. Delta Q is basically current charge equal to the previous charge. So you look at the charge in this, charge in this. Clear? Okay. So anytime you have doubts, again think of KCL. That is the basic. Good. So as of now we have seen a circuit that basically does this. It takes some input, scales it by a factor of k, and you get some scaled version. That is in continuous time. To give you an analogy, that is like taking some v of t, scaling it by some gain g. But as you know, even in continuous time, you get more useful and interesting things happening if you basically pass it through a filter. Instead of just a linear scaling, if you have an LTI filter with a transfer function h of j to pi f, is where you can build anything useful. So just like how you can do any linear filtering on continuous time signals, you can also do the same thing on these samples. So you can basically take this and pass it through a discrete time system with this frequency response. So again, going forward, we'll see in the next class how to make this. But today we'll look at how to analyze it. Right? Let us say I give you a circuit first. How do you analyze and find what is the frequency response? Again, it's again charge conservation and KCL. But one thing we should be careful when you are finding this frequency response is we should be clear as to what is defined as the time instant n. Okay? Because let's say this is my clock. Let's say I am looking at two clock phases, phi 1, phi 2. Fine. Now in practice, a switch capacitor circuit can have more than two clock phases also. But let's say we stick to two of them. Throughout this course, we follow the notation that the sampling instants are falling edge of phi 1. So falling edge of phi 1 is the sampling instant. That's the convention notation we'll follow throughout to be consistent. And let us say this instant is n times Ts. Okay. We will say any signal V of t sampled at this clock edge will be defined as V of t. That's all. Okay. So this is clear. Tell me what will be this time instant. One clock period earlier, that is n minus 1 times Ts. Fine. So which means what will be the signal sampled at this time instant? V of n. That's all. This is the notation we'll consistently follow. Okay. And also just for analysis, we'll define this time instant falling edge of phi 2 to be n minus half times Ts. I mean, it is not as though the spacing is Ts by 2, but just for notational purpose we do this. Right? When I say it's n minus 1 by half, it means that I am looking at the signal sampled in the previous clock phase, not on the previous clock cycle. Okay? I mean, in practice I can have multiple clock phases. If I say that I am looking at n minus 2 by 5, it means that I have a total of 5 clock phases. I am looking at the signal sampled 2 clock phases before. If I have phi 1, phi 2, phi 3, phi 4, phi 5, phi 5, yeah. If I am defining phi 5 as the sampling instant, that is NTS, 2 clock phases earlier, that is phi 3, that will be 2 by 5. To make sure that we can clearly define things. So which means signal sampled at this, we will call it as V of n minus half. Again, notice that this is all for our understanding. to the outside system, all that matters is v of n minus 1, n minus 2 and so on. Only the integer time instance, they are the samples of interest to us. The remaining things are all for our notational purpose. Clear? Cool. So yeah, so now let's look at one simple circuit. Let's say this is a full circuit. I have one. Yeah, okay, that's all. Okay. So let us say here again, this voltage across C2 is what I am defining as V out, and the same convention, signal sampled at the falling edge of phi 1 is V of n. Okay. So now I am interested to find what is my V out at the nth clock edge, and you want to find it as a function of the input, any previous values of the input and any previous values of the output. Because remember, when I look at a filter, the output at any time instant depends on, like all previous outputs and previous inputs also. It has a memory, which means I should be looking at the previous past also. So let's see how we can go about finding this. So the first thing is same, you draw the equivalent circuit in both clock phases. So let's quickly do that. So let's say in phi 1, the circuit is this. This is V in. And in phi 2, this is the circuit. Okay? Yeah.
Clock phases, you can assume that those clock phases are not.
No, yes, absolutely, yeah. Because the point is, every clock phase is there to configure the circuit in one particular mode. You don't want to mix multiple modes at the same time. Yeah, that's a good point. Yeah. So equivalent circuit is fine. So again, now I'm interested to find V out of n, and our convention is n is basically the falling edge of phi 1. So which of these two I should look at? Phi 1. Okay. So again, this voltage is what we are defining as V out. Okay. And we'll call this as some Vx. Again, one thing to have in mind is, when I go from one phase to the other phase, the circuit configuration changes. So the node connections you have in this clock phase will be completely different. Okay, so don't confuse with naming the same node voltages for different things. Better to have it separate. Okay. Cool. So now let's do this. We have to apply charge conservation here. So I'm interested to find V out. What is the charge conservation? Where will I apply charge conservation here? Huh? No, this is the circuit you are interested in. You want to apply charge conservation or KCL, whatever you want. Which node will you take? This is what you will take. And remember, I am interested to find V out of n. I will write it. So I apply charge conservation. So I have only one plate. I have V out of n times C2. So this charge should be equal to the charge in the same plate in the previous clock phase. Now again, we have to be very consistent with the time instance. Let me show you the clock. Nt is the previous clock phase, n minus half. Okay. We have two clock phases, which means if NTS is the current clock phase, the previous is n minus 1 by 2. Clear? So tell me, charge on this plate must be equal to charge on this plate. And what is the charge on this plate? Again, please be consistent with time. Vx of? Clear?
Isn't Vx, V out, n minus half.
Yeah, I mean the thing is, you don't, to avoid confusion, right? Like I told, the node connections change from one phase to the next phase. So you can have the same, nothing matters, but it's better to have it separate. We can say Vx of n minus half is same as V out of n minus half. That's okay. But I'm showing with the different names to make it a point that the nodes are different. Cool. So now to find V out of n, what should I find? My V out of n is Vx of n minus 2. So I should find Vx of n minus 2. So among these two, which circuit I look at now? The circuit in phi 2. So that is, I am looking at a time instant n minus half. Clear? So where will I apply charge conservation here? I just have one node. I should look at both capacitor charges. What is the charge? Vx of n minus half, remember, times C1 plus C2. Okay? Clear? This should be equal to the charge stored on the same plates in the previous clock phase. Okay? If the current clock phase I am looking at is n minus half, what will be the previous clock phase? N minus 1. Okay? Great. So tell me, what is the charge in the previous clock phase? I should look at the charge on these two plates. So what is the charge on this plate here? V in of n minus 1 times C1 plus V out of n minus 1 times C2. So that's it now. You guys know this is same as V out of n. So we already found it. So V out of n times, now it's all simple algebra, that it's okay, I'll just write it quickly because you can solve algebraic equations much better than me. So finally V out of n is V in of n minus 1 times C1 plus V out of n minus 1 times C2. This is the final thing. So again, remember, I mean, this is not that critical, you can do it. Important thing to understand is the two main charge conservation equations. Okay? So this is the final thing. Now if I want to find the frequency response h of e power j omega, from this, what do I do? I mean, this is Fourier transform. Yeah, I mean, let's say it's Fourier transform as of now. So you take the Fourier transform on either sides and then find the ratio V out by V in of e power j omega, right? I mean, you can do this again. I'll like directly write it. So I think you will get this as e power minus j omega C1 by C1 plus C2. Again, this is all minor algebra. I mean, don't worry about this. Okay. Just copy this. So yeah, just like in continuous time we had Fourier transform, and then to analyze stability and other stuff, you went to Laplace transform. So in discrete time, what do you have? Z transform. I'm sure you guys have learned or heard of it. I mean, if you don't know, it's fine. The only thing to notice Z is e power j omega. That's all. Okay. To find h of z, wherever e power j omega is there, I'll replace by z. So that basically gives me z inverse into C1 by C1 plus C2. That's all you need to know. This is just a final, Cool. So again, if I have x of n minus k, the Fourier transform is what? E power minus j omega k into x of whatever. In z transform, it becomes z power minus k times x of z. If you know this, it's enough. You will not go with other kind of region of conversions, blah blah blah. This much is enough. Cool. So now let me look at one other example, my favorite example to confuse students. So let's see. I remember it correctly. The triangle is a buffer, okay? Let's say this is a circuit we have. The triangle is an ideal buffer with a gain of 1. And as usual, I am interested to find V out. V out is the voltage across C3, and I am finding V out at the nth clock edge. Same convention at the end of phi 1 is what I am looking. This is a circuit. So as usual, let's draw the equivalent circuit in both clock phases. In phi 1, I have this. Okay. This is open. You can also draw it and then. Phi 2. Okay, this part should be trivial. Let me copy paste it. So equivalent circuit is fine. So again, let's look at the goal. Let me make some space. We are interested to find V out at the nth clock edge. So which of the two equivalent circuits I look at? This is V out. Phi 1. So I want to find V out. Where do I apply charge conservation? This is the circuit. At which node you apply? V out. Great, you start. So what is the charge stored on this plate? So can you, okay, can you try to write charge conservation at this node? Why? Okay. Remember that? Okay, hold on. Can others try and tell me if you can write charge conservation there? Which one? C2 and C1 meaning? No, what I'm asking is you're interested to find V out. So it makes logical sense to choose this node and write KCL or charge conservation. So if you try to write charge conservation at this node, what all will you take? Remember that KCL, so you look at the delta Q here, which means I'll consider the charge on this plate. But what about the current here? That is something that you do not know. The op amp, it's an ideal VCVS buffer. It can provide any amount of current. That is also an unknown to you, right? So again, this is like KCL, right? If you want to find this voltage, this is a buffer. What is this voltage equal to? Same as this guy, right? So let me call it, I don't know, V2 maybe. So from one, it's clear for me that V out of n is equal to V2 of n. That much is clear. So again, remember, whenever you have output of an op amp or a buffer like this, there is no point in applying KCL or charge conservation there, because you will end up with an additional unknown. Okay. Cool. So now tell me, I know that V out is equal to V2. So I need to find V2. Where will I apply charge conservation now? At V2. Here it's fine because this current is what? Current into the input of the buffer is 0. So no worries. So again, let me mark the time n. So V2 of n times C2, that will be equal to, let me call these voltages. Let's say this is V3 maybe, this is V4 something, okay. This is equal to what? V3 of, clear? So which means now to find V2, I should find V3 of n minus half. So which circuit I'll now look at? This is the circuit I should be looking at, clear? So I'm interested in n minus half. Erase all this. And where will I apply charge conservation now? Can I apply here? Again, you have the same issue. So, and you already know V3 of n minus half is equal to what? That's all. Great. So now you have to find V4 of n minus half. Where do you apply charge conservation? Yeah, let's write it clearly, right? You are correct. Let's write it in a formal way. To find V3 of n minus half, I should find V4 of n minus half. This is the thing. I'll apply KCL or charge conservation at this node. This current is 0, so no worries. So if I look at V4 of n minus half times C1 will be equal to, yeah, this is n minus 1. Okay. So now of course you can easily see V out is equal to V2, V2 is V3, V3 is V4, V4 is, so what is V out of n? That's all. Yeah. Is this clear? No C1. Nothing should come. Everything should get cancelled. I mean, remember, if I do this, everything gets cancelled, right? I mean, okay. Is this clear? This is an example I like because kind of clear some confusions on where to apply KCL, where to apply charge conservation. Okay. So again, so now you see that this is
So you progressively apply KCL at all nodes and see that what will be the result.
Yeah. Again, when you're applying, you make sure that you're not applying at the output of a voltage source because that current is unknown. That's all. And the moment you have a voltage source or a VCVS, that output voltage is defined by something else, so you can directly write it. So now you see the output is essentially one clock cycle delayed version of the input. So if you have something simple like this, you should go back and stare at the circuit and see if the circuit is talking to you. Of course, it will not talk. What happened? Okay. Some nightmare. Okay. Let me try to copy paste it. So let's try to make sense of this, right? So let me draw the clock faces. I'll just draw one master clock and okay. So let us say this is clock phase phi 1, phi 2, phi 1. Let me call this as first edge. So let us say during the first clock edge, input is sampled on C1. So I will say Vin is sampled on C1. Then phi 2 happens. During the next phi 2, what's happening? I mean, let's start from, let's assume all capacitors are uncharged first, right? If everything is 0, first I am sampling Vin on C1. So at this edge, it's there. During the second clock phase, what happens? Yeah, Vin is basically buffered and that gets stored on C2. So at the end of this phase, Vin is available on C2. Now in the next phase, what happens? This is active. What happens? What is the voltage across C2 now? Vin. The same Vin is buffered and then pushed on to C3. Is that clear? So at this point, this is when Vin is available on Vout. I mean on C3, or that's basically Vout. Clear? So from the point you have sampled it to the point you have taking the output, there is obviously one clock cycle of delay. And of course, it turns out, I mean, not turns out. So this is one way to generate or create a delay for analog signals, and these are, in the recent times very popular for creating what is called beamforming systems. Beamforming, loosely speaking, is where, I mean, if you have an antenna, it transmits in all directions. Now let us say I don't want to transmit everywhere. I want to transmit only to him. So I'll make sure all my beam is directed towards him. So it turns out we can do this by using basic interference. If you add signals with proper time delays and proper phase shifts, you will have constructive interference. Other places you have destructive interference. So which means you should delay the signal and add it with appropriate gains. That's the basics of constructive and destructive interference, right? For that you need a delay line, and this is one nice way of generating delay. So you can basically do this.
In the previous block,
Yes, yes.
after 5,
They can't go. Tell me.
after 5 the gain is like stored at 5 right? Sorry, at C3.
See, yeah, correct.
So, like, won't the progressive, after progressive clock cycles, the V will get added on?
No, that's what, right? Yeah, it's a good point. He's saying right now, let us say V out consists of V in of n. The next clock cycle, he's saying the next V in will get added. Do you think that will happen here? I mean, let us say I make the connection in phi 1. Okay, this is the equivalent circuit. Assume that the capacitor already has some, let us say, some 1 volts. Now I am putting in V in here. What will be the voltage here? V in. The initial voltage on the capacitor, that will actually get discharged to the buffer. This voltage buffer is ensuring that whatever is here is exactly mirrored there. Even if the capacitor stored something, even if it remembered anything, doesn't matter. Because ideally, what is the output resistance of an buffer? Output resistance. Output resistance is 0. Buffer is a voltage controlled what source? Voltage source. So output resistance of a voltage source is 0. So this has a 0 output resistance. So from the output side, if you see, you have R and a very small resistance. So it instantly discharges. Any initial voltage you have, that will instantly discharge, and whatever you have current, that will only get added. Okay. So yeah, so I was saying one way to get delay is this. So you can do this: sample the input in one clock phase, and you take the output in another clock phase. Right? That is, let us say if I have a clock like this, this is, let us say, phi 1, and this is basically Ts. You sample the input at the end of this, but you transfer this in another clock phase like this. Now you see that you have so much of data. So in practice, you can have multiple phases of clocks. You can have multiple clocks like this for phi 2. And depending on what clock you feed in here, the delay can also be programmed over one clock period of Ts. Okay. Of course, variations of this is used, but yeah, can also. Okay, and see, of course, now you know this. Now you know that this circuit is providing one clock cycle of delay. If, let us say, you find some other circuit, you should be able to identify the circuit and try to make sense of what's happening. Like for example, let us say add some things to this, right? Let us say I do something here, and then let's say let's say then so again, you can, as usual, you can go and solve using charge conservation, but you already know what this portion is doing, so you should be able to kind of make quick guesses. So can you first tell me, if I have V in here, what will be the voltage here at the nth clock instance? So basically this much is already known to me, I don't have to do anything. And remember, this is not affecting my C3 till phi 1. Whatever I am adding extra is not also affecting my previous circuit. So this much I know, it's V out of n minus 1. Okay. So let me draw the clocks. So let us say this is phi 1, phi 2, and so on. This is, let us say, nth clock instant. Here I know that across C3 I have V in of n minus 1. Fine. Across C4, what will be the voltage? At the nth clock instant, what is the voltage across C4? V in of n. Yes. C4 is sampling V in of n. So till this point it's clear, straightforward. Right? Now let us say what happens in the next clock phase phi 2. In the clock phase phi 2, You are basically putting the two capacitors in parallel like this. Yeah, in this clock phase, maybe I'll show. You have equivalent circuit like this. C4 had an initial voltage of V in of n. This had V in of n minus 1. And let us say for simplicity C3 is equal to C4 also. So what will happen now? Yeah, you can do charge conservation, it's going to get averaged. At the end of phi2, C3 or C4, whatever, will have V in of n. Okay. So, which means what will be the voltage across this capacitor C5? Yeah, during phase 2, the same thing is happening, right? Whatever voltage you have here, that is buffered and stored on C5. So, C5 also has the same thing. Okay. So, that this is fine. Now, in the next clock phase, this is activated. So, here is where the next thing happens, and what is that voltage? What will happen here? C6 will get same as C5, right? And if this is n, what is this instant? Okay. So, if this is my final output, V out, I know at n plus 1th instant, the voltage it has is, that's all. Again, this is one way of basically, if you know some things by parts, you like try to guess what is the overall operation. That's basically how you do, right? I mean, any circuit for that matter, you can solve using KCL, KVL, but you learn all Thevenin's, Norton's, substitution theorem, blah blah blah. Why? For every circuit, you don't want to sit and solve using KCL. If you know some other things, you can, by inspection, you can say some comments. So one last thing, so I will show you one circuit. Please try to solve for that. Let's say I have 2-3 minutes. Okay. It's an extension of the circuit we saw. So 1 to 1, C1, C2, C3. This is V in. As usual, I'm interested to find what is V out of n at the end of phi 1. So, I mean, more than the final expression, can you write the charge conservation equations and tell me, right? Final is all algebra. So, I'll pause the video. So, we have 2-3 minutes. Please try to work out.